Optics for communications in control of robotic arms. Hi, this is Terrance Wei.
Hi, this is Xin Jing.
Hi, this is David Vazquez.
This is our senior project for ECET under advising by Professor Farbod. And here is our table of contents for our senior project design. The main idea behind this project is that we are trying to demonstrate what we have learned throughout our academic career at Cal Poly Pomona. We are also working alongside with Professor Farbod and his project. We are trying to implement this system into his. And here's the main frame for our project. We are using motors to move various parts of the system. We are using a 3DOF robotic arm to move items. And we are also developing our own software and writing codes on our own. And by combining it, we will be creating a workcell-like environment. That is our project goal. Here is our workflow of the project. First, the signal is being detected by the Raspberry Pi 4. Then it's being processed into different commands. Then it will turn on the Pi camera and detect if there's anything on the conveyor belt. Then it sends a feedback into the Raspberry Pi 4. It then communicates with a nuclear processor. The conveyor belt moves the item on the belt to a desired location. 3DOF robotic arm then will pick up the object and put them into the right place. Next, we are going to talk about some of the project components that is available for us readily on the market. Raspberry Pi 4 is our central processor. It processes most of the information, including the signal being received, signal that needs to be sent out, and the feedback coming from the camera. We are giving it a Pi camera, so it has a ability to detect the basic shapes and color, making it more reliable to receive information. We are using a 3DOF robotic arm. This robotic arm will be controlled by a secondary processor, nuclear microprocessor.
Nuclear board and motor drive. This development board is the core control of the transmission system. As a basic part of connecting the whole project from identification model to signal receiving model, the conveyor belt should respond to control signals. At the same time, the conveyor belt should be able to be used as an independent work unit for people to operate. We achieve it through the development board with the motor drive. Photo-sensitive sensor. Set the light sensor in the object recognition area. When the object in this area, it will block the light source. The light changer causes the photosensitive model to output signals to the development board. Then the development board will stop the conveyor belt, give the camera model enough time to work. We set this part in order to realize the real-time response of the transmission system in the project. In Plan B, we can skip this model, let the camera system directly transmit signals to the development board. Such a design can also achieve real-time response.
Next, we are going to talk about some of the hardware design. This is a signal receiver. The PCB design is developed by using Eagle software. It can detect a LED signal coming out of a laser detection. So after creating the PCB, we also need a container for it. And in this case, we are using the 3D printing technology. I have developed this design in the SolidWorks software.
In the beginning, when we were looking for ideas that would help us control the conveyor belt, we were inspired by a circuit which we learned from one of our classes. That is the relay-controlled DC motor design. Each relay is a 24-volt rated device which opens and closes its contacts whenever the relay coil gets powered. For this circuit, we would however need two power supplies, one for the motor and another for the relays. To the right, you can see the ladder diagram schematic. Alongside with the schematic, you could also see the H-bridge, which will help us control the direction of the motor. Here we have a detailed circuit board for our relay controller design. To do this, we use the PCB design software Eagle. This program allows us to create separate boards specifically for our circuit design instead of needing to use our breadboards. On the left, we have the schematic for the board. The schematic was done using the ladder diagram before. On the right side, we have our board layout. Within the board to the left, we have our inputs for our power supplies. Next, we have our forward and reverse buttons. On top of that, we have our main stop switch. Next, we have 4 relays. And under that, we have the inputs for our motor. However, because we are experiencing this new way of life, we were not able to realize the order for this board. We also discussed issues with not being able to control the motor speed on its own. This is why we look towards controlling our conveyor belt through a different method.
Conveyor belt main kit, motor, electric type, driver shift bearing. We chose the RS555 DC motor. The normal voltage of the motor is 12 voltage. No load RPM is 6,100. Steel current is 9.2 amp. Steel torque is 23 ounce per inch. This is the best DC motor we can choose in 12 voltage level. We can see these graphs. The graphs show us the motor has greater torque. In half load, it can reach 12 ounce per inch torque. In this project, we are not pushing speed. We need to transport objects smoothly. So this motor provides high tolerance for our project. We made the track of electric type. For a track of the conveyor system, we need a material with elasticity and suitable friction to ensure that it can grasp the driver shift and transfer objects. About the driver shift, that is a good way to conversion of the mechanical engineering from the motor to belt. Conveyor belt, basic hardware, 100% handmade model with a high selectable range. Support and connect the whole project.
Next, we are going to talk about the software development. This is the main part of the code for signal receiver. It is detecting a 01 or 10 coming out of 2 LDRs. It then gets put into an array of data, and then it will be sent to a case statement selection, and then ready for next part. Here are some of the main codes for our color detection and pi camera. We are trying to detect a green color in a frame by applying a mask over it, and now only the green color will show, and by doing so, we can also do a shape recognition.
Code for conveyor belt system. We program it in C++ language. This program can control the speed, direction, and working time of the motor. We use a loop that a conveyor belt can be continuous. When input signal appears, it
Here
will
is our
stop
Rudolph
the
robotic
motor.
arm development. We are using MATLAB Simulink to do the inverse kinematics and controlling the robot arm. Now next, please allow us to show you the final product. Here is a SolidWorks model of a representation of our project. The setup of robotic arm, and the setup of a signal receiver and camera, setup of the conveyor belt,
Now we move on to the lens motor control design. Here we were tasked to see if we could create a device which would help rotate the lens automatically. This is the RSP1X225 rotation mount. For our project, we were only interested in rotating the lens from about 0 to 90 degrees, because this would change the input for our overall project. However, because of this new way of life that we experienced during the semester, we were no longer able to go to the lab for testing. Luckily, we were able to get a SOLIDWORKS design for the exact part and began designing a prototype. To begin working on this, we first looked at what would make the lens rotate. We knew that the lens had teeth around its inner ring, so we started creating gears to help match the teeth. As you can see in the images on the bottom, we did create a gear that matched pretty well to the device. However, this gear would have to be adjusted through further testing. Next, we looked at what kind of motor would help us best rotate the gear. Wanting to keep things simple, we started off our design using a servo motor. The image on the left shows how the motor would help drive the small gear to then move the second gear, which would then allow us to rotate the lens in any direction. This method would allow for us to rotate the motor from 0 to 180 degrees and still get the driver gear to work in full rotation. However, we encountered some issues with the gears not being practical due to the size of their teeth, so instead we designed new gears with proper teeth shown on the top right, except we were not able to simulate the basic motion because throughout the simulation the prismatic arm would get jammed. So looking at these issues, we decided to look into using a different motor. So then we looked at using a small DC motor. This would allow for us to connect any gear to the center and give us better control overall. Our DC motor at hand even had a small spur that could attach to a gear. There was also no need for the prismatic joint from using the servo motor. Along with better control of the system, the DC motor requires more hardware. For that, we would be needing an H-bridge to control the direction and other small components that would allow us to also adjust the speed of the motor. Required for this system, we would use Arduino programming, we would use the L298N motor driver, and other small components. Comparing this with the servo motor, the added L298N motor driver allows for speed control, forward and reverse control, compatible with Arduino, and the design is compact. Here we have a compound gear train where all the gears except gear E have a certain number of teeth. Gear A will be our driver and the rest are going to be the driven gears. Our gear reduction will allow for the output to be much slower, which will be needed for precision. However, since we are going to be using our DC motor, we have the availability in programming to control the speed, which also controls precision. For the moment, gear E does not have teeth because this would be adjusted if we were to practically 3D print the build and test it with the actual lens. After a ton of edits, we chose to go with the DC motor. This is the latest idea and look for our lens motor control. Again, because of this new way of life that we are experiencing, we were not able to reproduce the device and test for adjustments. This is only in simulation and theory of how the device can work in the simplest method. The orientation and design also has room for improvement when looking to practically mount it next to the lens device.
And this concludes our senior project presentation. Thank you.